Tonight, we are going to talk about something almost impossible to imagine. A planet so large that it challenges everything we thought we knew about planetary physics. A world so massive in size that you could fit our entire solar system's largest planet inside it and still have room left over. And yet, this giant weighs so little for its size that it would float in water if you could find an ocean big enough to hold it. Now, you have probably heard about big planets before. Jupiter is the giant of our own solar system, and we have been studying it for centuries. But this distant world makes Jupiter look modest. If Jupiter were the size of a grapefruit, this planet would be the size of a watermelon. And it sits over 1,000 light years away from us, orbiting a star that most people have never heard of, in a region of space we are only just beginning to explore. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, into the story. To understand why this discovery matters, we need to start with some history. For most of human existence, we only knew about the planets in our own solar system. Mercury, Venus, Mars, Jupiter, Saturn. These were the wandering stars that ancient people noticed moving against the background of fixed stars. Later, we discovered Uranus, Neptune, and for a while, Pluto. But all of these planets orbit our star. We had no idea if other stars had planets too. For centuries, astronomers assumed they probably did. It would be strange if our star was the only one with a family of worlds circling around it. The universe seemed too big, too full of stars, for us to be that special. But assuming something exists and proving it exists are two very different things. Finding planets around other stars is incredibly difficult. Think about it this way. Imagine you are standing in Los Angeles and someone asks you to spot a firefly hovering next to a lighthouse in New York. That is roughly the challenge astronomers face when searching for exoplanets. Stars are blindingly bright. Planets are tiny by comparison and produce no light of their own. They only reflect the light of their parent star, and that reflected light is billions of times dimmer than the star itself. Then, in 1992, everything changed. Astronomers discovered the first confirmed exoplanets, but they were not orbiting a normal star like our own stellar neighbor. They were circling a pulsar, the rapidly spinning remnant of a dead star that had exploded in a supernova. This was exciting, but pulsars are extreme objects. Finding planets around one of them did not tell us much about whether normal stars had planetary systems. The real breakthrough came in 1995, when astronomers Michel Mayor and Didier Queloz announced they had found a planet orbiting a sun-like star called 51 Pegasi. This planet was nothing like anything in our solar system. It was a gas giant, similar in mass to Jupiter, but it orbited incredibly close to its star, so close that it completed an orbit in just over 4 Earth days, so close that its surface temperature was over 1,000 degrees. This discovery shocked the astronomical community. Nobody expected to find a Jupiter-sized planet so close to its star. In our solar system, gas giants like Jupiter and Saturn orbit far from our star, in the cold outer regions where ice and gas could accumulate during the solar system's formation. Finding one practically hugging its parent star was like finding a polar bear in the Sahara Desert. It should not be there. And yet, there it was. This planet, and others like it discovered soon after, became known as hot Jupiters. They were the first type of exoplanet we found in large numbers, not because they are the most common type of planet in the universe, but because they are the easiest to detect. A massive planet orbiting close to its star creates a bigger wobble. It blocks more light when it passes in front of the star. It leaves bigger fingerprints for our instruments to find. And this brings us to how we found the largest planet ever discovered. The discovery came through a method called the transit technique. This works on a beautifully simple principle. When a planet passes between its star and Earth, it blocks a tiny fraction of the star's light. If you are watching that star carefully, measuring its brightness over time, you will see a small dip as the planet crosses in front. The star dims slightly, then returns to its normal brightness as the planet moves away. The amount of dimming tells you how big the planet is relative to the star. A bigger planet blocks more light. And the timing of these dips tells you how long the planet takes to complete one orbit. This is where the HAT project comes in. HAT stands for Hungarian-made automated telescope, and it is a network of small telescopes designed specifically to search for transiting exoplanets. The project started in 2003 with a single telescope in Arizona. Over the years, it expanded to include telescopes in Hawaii, Arizona, Namibia, Chile, and Australia. This global network allows astronomers to watch stars almost continuously, catching transits that happen at any time of day or night. The telescopes themselves are not particularly large. Each one has a lens about 4 inches across, roughly the size of a high-quality amateur telescope. But what they lack in size, they make up for in automation and dedication. These telescopes observe hundreds of thousands of stars every night, measuring their brightness with extreme precision, looking for the telltale dips that indicate a transiting planet. Between 2005 and 2008, the HAT network collected observations of a star in the constellation Hercules, about 1,044 light-years from Earth. The telescopes noticed that this star was dimming periodically. Every 4.81 Earth days, the star's brightness dropped by about 2.5%. That is a large dip. For comparison, when Jupiter transits across the face of our star, as seen from a distant star system, it would block only about 1% of the light. Something was passing in front of this distant star, and whatever it was big. After years of follow-up observations to rule out false positives and confirm the discovery, the planet was announced in 2017. And as astronomers analyzed the data, they realized they had found something extraordinary. Here are the key facts about this world, stated clearly and precisely before we explore their implications. This planet is roughly 2.1 times the diameter of Jupiter. If Jupiter is about 88,000 miles across at its equator, this world stretches to nearly 185,000 miles from one side to the other. You could line up about 23 Earths across its diameter. By volume, you could fit roughly 12,000 Earths inside this single planet. It is the largest confirmed exoplanet ever discovered by radius. But here is where things get strange. Despite being more than twice Jupiter's size, this giant is only about 0.45 times Jupiter's mass, according to the most recent measurements published in 2025. Let that sink in. This planet is more than twice as big, but weighs less than half as much. That means its density is astonishingly low, only about 0.06 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. This planet would float in water like a beach ball in a swimming pool. The planet orbits an F-type star, which is hotter and more luminous than our star. This host star is about 1.6 times our star's mass and about 1.85 times its diameter. At a distance of only about 7 million miles, the planet completes one orbit in just 4.81 Earth days, racing around its star at tremendous speed. At that distance, the equilibrium temperature of the planet is approximately 1,900 Kelvin. Now, Kelvin is the temperature scale scientists use, where 0 is absolute zero, the coldest possible temperature. 1,900 Kelvin translates to about 2,960 degrees Fahrenheit, or roughly 1,620 degrees Celsius. That is hot enough to melt most metals, hot enough that the planet glows with its own thermal radiation. This world is being cooked by its star every moment of its existence. So how can a planet be so big yet so light? This is one of the most interesting questions this discovery raises. Jupiter, the giant of our solar system, is mostly hydrogen and helium. These are the two lightest elements in the universe. Hydrogen makes up about 90% of Jupiter's mass. Deep inside Jupiter, the pressure becomes so intense that the hydrogen behaves in strange ways. Near the center, hydrogen is crushed so tightly that it becomes metallic, conducting electricity like a metal despite being made of the lightest atoms. This distant giant is also made mostly of hydrogen and helium. But unlike Jupiter, it is not compressed into a dense ball. Instead, it is puffed up like a marshmallow that has been heated in a microwave. The same amount of material is spread over a much larger volume, resulting in that incredibly low density. The intense heating from the nearby star is the primary cause of this inflation. When you heat gas, it expands. This is basic physics. The molecules in a gas move faster when you add energy to them, and they spread out to occupy more space. On Earth, this is why hot air balloons rise. The air inside the balloon is heated, it expands and becomes less dense, and it floats upward through the cooler, denser surrounding air. Now scale that effect up to a planet. The upper atmosphere is being constantly bombarded by radiation from its nearby star. That energy heats the gas, making it expand. Over billions of years, this heating has caused the planet to inflate dramatically. But simple heating models do not fully explain the extreme puffiness we observe. Something else must be contributing. Scientists have proposed several additional mechanisms. One possibility involves the planet's orbit. If the orbit is slightly elliptical rather than perfectly circular, the star's gravity would squeeze and stretch the planet as it moves closer and farther during each orbit. This tidal flexing generates heat through friction, similar to how bending a paperclip repeatedly makes it warm. Over billions of years, this tidal heating could pump considerable energy into the planet's interior. Another possibility involves the planet's magnetic field. Gas giant planets often have strong magnetic fields, and these fields can interact with the stellar wind, the stream of charged particles constantly flowing out from the star. This interaction could create electrical currents in the atmosphere, and these currents could deposit energy deep in the planet, heating it from within. A third explanation suggests that certain layers in the atmosphere might trap heat, preventing it from escaping efficiently. This could cause the interior to stay hotter than expected, keeping the planet inflated. The honest answer is that we do not fully understand why this planet is quite so puffy. It is one of the open questions in exoplanet science, a mystery that astronomers are actively working to solve. This world, as one of the most extreme examples of an inflated planet, is a valuable laboratory for studying this phenomenon. At such a close distance to its star, the planet is almost certainly tidally locked. This means one side always faces the star, while the other side always faces away into the darkness of space. The moon is tidally locked to Earth in the same way, which is why we always see the same face of the moon. This creates dramatic conditions. The day side, the hemisphere facing the star, is constantly bombarded by radiation. Temperatures there reach thousands of degrees. The night side, facing away from the star, receives no direct starlight. It should be much cooler, though heat transported from the day side by atmospheric circulation prevents it from becoming truly cold. The boundary between day and night, called the terminator, would be a zone of constant twilight. Winds blowing from the hot day side to the cooler night side would race across this boundary, possibly reaching speeds of thousands of miles per hour. The atmosphere is probably a violent, churning maelstrom driven by the temperature differences between the perpetual day and perpetual night. Now, when we talk about the atmosphere of this world, we need to understand that we are not talking about anything remotely like Earth's atmosphere. There is no breathable air. There is no oxygen in any real quantity. The atmosphere is probably dominated by hydrogen and helium, the same elements that make up most of the planet's bulk. But at temperatures approaching 3,000 degrees Fahrenheit, exotic chemistry becomes possible. Many substances that we think of as solids or liquids become gases. Titanium oxide and vanadium oxide, compounds used in paint and industrial processes on Earth, might exist as gases floating in the atmosphere, absorbing starlight and heating the upper layers even further. Some scientists think that the hottest gas giants might have atmospheres where iron and magnesium exist as vapor. Iron, one of the hardest common metals, reduced to a gas and floating in the atmosphere. On the scorching day side, it might literally rain iron droplets as the metal condenses in slightly cooler regions and falls through the atmosphere. There might also be silicate clouds. On Earth, silicates are rocks. Granite, sand, glass, these are all silicate materials. But at these temperatures, silicates could vaporize and then condense into clouds. These would be clouds of rock dust, floating in a hydrogen-rich atmosphere, drifting on winds that howl at supersonic speeds. The colors of this world are probably nothing like anything we see on Earth. Depending on what chemicals are present and how they absorb and reflect light, the planet could appear dark, almost black, absorbing most of the starlight it receives. Or it could glow with strange colors as hot gases emit their own light. Without being able to directly photograph the planet, we can only speculate based on our models and our observations of similar worlds. Finding this planet and measuring its basic properties was just the beginning. To truly understand this world, astronomers want to study its atmosphere directly, and remarkably, we have techniques that can do exactly that. When the planet passes in front of its star, some of the starlight filters through the atmosphere before reaching us. Different gases absorb different wavelengths of light. By carefully analyzing the spectrum of starlight during a transit, astronomers can identify which wavelengths are being absorbed and which gases are present. This technique, called transmission spectroscopy, has been used to detect water vapor, sodium, potassium, and other elements in the atmospheres of exoplanets. This giant world, with its enormous size and puffed-up atmosphere, is an excellent target for transmission spectroscopy. A larger atmosphere means more gas for starlight to pass through, which means stronger spectral signatures. The James Webb Space Telescope, launched in 2021, has the capability to study this planet's atmosphere in unprecedented detail. What we learn from this discovery will help us understand the entire class of inflated hot Jupiters. These planets are some of the most extreme worlds in the universe, pushed to the limits of what planetary physics allows. By studying them, we learn not just about those specific worlds, but about the processes that shape all planets everywhere. To understand what makes this particular discovery special, it helps to compare it to other planets we know. Jupiter is the giant of our own solar system. It is the largest planet orbiting our star, containing more mass than all the other planets combined. If you hollowed out Jupiter, you could fit about 1,300 Earths inside. Jupiter has at least 95 known moons. It has a famous Great Red Spot, a storm larger than Earth that has been raging for centuries. Jupiter is magnificent. But this distant world is more than twice Jupiter's diameter. You could fit roughly 9 Jupiters inside by volume. The scale difference is enormous. Consider some other giant exoplanets for comparison. WASP 79b is another inflated hot Jupiter, orbiting a star about 790 light-years away. It is about 2 Jupiter radii in diameter, making it large but still smaller than our subject. WASP 17b, discovered in 2009, was for a time considered the largest known exoplanet. It is roughly 1.89 times Jupiter's diameter. Still smaller. There is Kelt 9b, one of the hottest known exoplanets, with a dayside temperature exceeding 7,800 degrees Fahrenheit. That is hotter than some stars. Kelt 9b is about 1.89 times Jupiter's diameter. Hot, extreme, but still not as large as what we are discussing tonight. There have been candidates that might be larger, but many of these turn out to be brown dwarfs upon closer inspection. Brown dwarfs are objects that fall between planets and stars. They are too small to sustain hydrogen fusion like true stars, but they are more massive than planets, typically at least 13 times Jupiter's mass. Some brown dwarfs are puffy and large, but they are not planets. This record-breaking world, at roughly 0.45 Jupiter masses according to the latest measurements, is definitely a planet. It does not have nearly enough mass to be a brown dwarf. It is simply a planet that has been inflated to an extraordinary degree by the intense radiation of its parent star. Now, you might wonder, how big can a planet get? Is there a limit? The answer is yes. There are limits, and they are set by physics. As a gas giant grows more massive, something counterintuitive happens. Adding more mass does not necessarily make the planet larger. Instead, the additional gravity compresses the existing material, making the planet denser. Jupiter is actually close to the maximum size a gas giant can reach through adding mass alone. If you added more hydrogen and helium to Jupiter, it would not get much bigger, it would just get denser. The planets that exceed Jupiter's size do so not because they have more mass, but because something is puffing them up. Remove the intense stellar heating from this distant giant, let it cool down over billions of years, and it would contract to a size similar to, or even smaller than Jupiter. This is why inflated hot Jupiters are such interesting objects. They show us how external factors can dramatically alter a planet's structure. The same amount of matter can take vastly different forms, depending on circumstances. This giant planet probably did not form where we find it today. At 7 million miles from its star, the protoplanetary disk was too hot for ices to condense. There was not enough solid material to build a massive core quickly. And yet, there it is, a gas giant in an orbit that should have been impossible. The leading explanation is that this world formed much farther from its star, out in the cold regions where gas giant formation is possible, and then migrated inward. This migration probably happened through interactions with the protoplanetary disk itself. As the young planet orbited through the disk, gravitational interactions with the gas created spiral density waves, areas where the gas was slightly more or less dense than average. These density waves pulled on the planet, draining angular momentum from its orbit. Losing angular momentum means falling closer to the star. Over millions of years, the planet spiraled inward from the outer reaches of the planetary system to its current scorching orbit. This process, called Type II migration, is thought to be common in young planetary systems. Many hot Jupiters probably reached their current positions through this mechanism, but the details vary from system to system. Some planets migrate quickly and end up very close to their stars. Others migrate more slowly or stop partway through. Some might even migrate outward rather than inward, depending on the specific conditions in the disk. There is also the possibility that other planets in the system influenced the migration. If there are additional planets that we have not yet detected, their gravitational interactions could have modified this planet's orbit over time. These interactions could pump up the orbit's elongation, increasing tidal heating, or they could have helped push it into its current position in the first place. The system is still being studied. Future observations might reveal additional planets. They might detect small variations in the giant's orbit that hint at gravitational influences from unseen companions. The system might turn out to be more complex than we currently realize. One of the fascinating questions about hot Jupiters like this one is how long they can survive. These planets exist in precarious situations. They orbit so close to their stars that they experience extreme conditions. Some hot Jupiters are slowly losing their atmospheres, the intense stellar radiation stripping away their outer layers and sending gas streaming off into space. Over billions of years, this could greatly reduce a planet's mass, potentially transforming a gas giant into a bare, rocky core, or even destroying it entirely. This planet's extremely low density might make it particularly vulnerable to atmospheric loss. Its gravity is relatively weak for a gas giant because it has so little mass spread over such a large volume. The escape velocity, the speed gas molecules need to reach to escape the planet's gravity, is lower than for a denser planet. This means it is easier for atmospheric gas to be stripped away. However, this world is relatively far from its star compared to some ultra-hot Jupiters. There are planets that orbit their stars in less than a day, experiencing even more intense radiation. Some of these ultra-short period planets are actively evaporating, with observations showing tails of gas trailing behind them as they orbit. This planet, with its nearly 5-day orbit, is not in immediate danger of evaporating away. The host star is also relevant here. F-type stars are brighter than our star but have shorter lifespans. They burn through their hydrogen fuel more quickly. This star is estimated to be about 3 billion years old and probably has several more billion years of stable life ahead of it. But eventually, it will exhaust the hydrogen in its core and begin evolving into a red giant. As it swells, it will engulf any planets in close orbits. The planet, for all its enormity, will eventually be consumed by its own star. This is the fate of many planetary systems. Our own solar system will experience something similar in about 5 billion years when our star begins its transformation into a red giant. Mercury, Venus, and possibly Earth will be consumed. Every planetary system has an expiration date set by the lifespan of its star. This giant world exists now, in this particular moment in cosmic history. A billion years from now, it might look very different. 2 billion years from now, it might not exist at all. We are fortunate to be able to observe and study it during this window of time. The distance to this distant world is almost impossible to truly grasp. The planet is about 1,044 light-years away. A light-year is the distance that light travels in 1 year, and light is the fastest thing in the universe. It moves at about 186,000 miles per second. That means light can travel around Earth about 7.5 times in a single second. It can cross the distance from Earth to the Moon in about 1.33 seconds. But even at this incredible speed, light takes time to cross the vast distances between stars. Light from our star reaches us in about 8 minutes and 20 seconds. Light from Proxima Centauri, the nearest star beyond our solar system, takes about 4.25 years to reach us. Light from this distant world takes over 1,000 years. When we look at this star tonight, we are seeing it as it was 1,000 years ago. The light entering our telescopes has been traveling through space since around the year 1000. The Norman conquest had not happened yet. The first universities in Europe would not be founded for another century. The Crusades had not begun. That is how long that light has been traveling to reach us. This means we are always looking into the past when we observe distant objects. For this distant planet specifically, the observations we make today show us the planet as it was over 1,000 years ago. If something dramatic happened to that planet yesterday, we would not know for another 1,000 years because the light carrying that information has not reached us yet. The distances between stars also create total isolation. Even if we could travel at the speed of light, which physics tells us is impossible for objects with mass, reaching this world would take over 1,000 years. With any technology we can currently imagine, the journey would take much longer. Voyager 1, the fastest spacecraft we have ever sent out of the solar system, travels at about 17 miles per second. At that speed, reaching this star would take over 11 million years. These distances mean that detailed exploration of this planet is beyond our reach with current technology. We cannot send a spacecraft to visit. We cannot collect samples. We cannot take close-up photographs. Everything we know about this distant world, we have learned by carefully analyzing the tiny amount of light that reaches us across 1,000 light-years of space. And yet, despite these incredible distances, we know quite a lot. We know the planet's size. We know its mass. We know how long its year is. We know the temperature of its atmosphere. We are beginning to understand its chemical composition. This shows the ingenuity of astronomers and the power of modern technology. From faint starlight, we can deduce the properties of a world so far away that no human will ever visit it. You might wonder why astronomers are confident about these measurements. After all, we are talking about a planet over 1,000 light-years away. How can we know its size, its mass, its temperature with any confidence? The answer lies in the rigorous methods of modern astronomy and the independent verification that comes from multiple techniques giving consistent results. The transit method, which revealed this planet's size, works on basic geometry. When the planet passes in front of its star, it blocks a certain percentage of the starlight. The amount of blocking depends on the ratio of the planet's cross-sectional area to the star's cross-sectional area. This is simple geometry, nothing more complicated than calculating how much of a wall is covered when you hold up a ball in front of a light. We know how big the star is from several independent measurements. Stellar models, which are extremely well tested from over a century of stellar physics, tell us how size, temperature, and brightness relate for different types of stars. Spectroscopic analysis reveals the star's temperature and chemical composition. The star's distance, measured through parallax and other techniques, allows us to convert apparent brightness to actual luminosity. All of these measurements are consistent and point to a star about 1.85 times the diameter of our own star. Given the star's size and the amount of light blocked during transits, simple geometry tells us the planet's size. The calculation is straightforward and has been verified countless times with other planets where we have additional information. The planet is about 2.1 times Jupiter's diameter. This measurement is solid. The mass measurement comes from a different technique entirely. The radial velocity method measures how the star wobbles due to the planet's gravitational pull. As the planet orbits, it tugs on the star, causing the star to move in a small circle or ellipse. This motion causes a Doppler shift in the star's light, a tiny change in the wavelengths of light that reveals how fast the star is moving toward or away from us. The size of this wobble depends on the planet's mass and how close it is to the star. A more massive planet produces a bigger wobble. A closer planet also produces a bigger wobble because the gravitational force is stronger at shorter distances. By measuring the wobble and knowing the orbital distance from the transit timing, we can calculate the mass. Both techniques, transits, and radial velocities give consistent results. The orbital period measured from the transit timing matches the orbital period inferred from the radial velocity curve. The mass and size are consistent with a gas giant of extremely low density. Everything fits together. Similar techniques have been validated many times on other systems. We have compared transit measurements to direct imaging measurements where possible. We have used asteroseismology, the study of stellar vibrations, to independently verify stellar sizes. We have tested our mass measurements against binary star systems, where we can measure masses directly from orbital dynamics. The science is mature and reliable. We can have high confidence that this planet really is as large and as low density as we claim. Future observations will likely reveal much more about this distant giant. With the James Webb Space Telescope, astronomers can perform detailed spectroscopy of the atmosphere during transits. As the planet passes in front of its star, starlight filtering through its atmosphere will carry the fingerprints of whatever molecules are present. Water vapor, carbon dioxide, methane, sodium, potassium, titanium oxide, vanadium oxide, all of these leave distinctive marks in the spectrum of light. By identifying these marks, we can inventory the atmospheric composition. We might also be able to study the temperature structure of the atmosphere. Different layers absorb and emit light at different wavelengths. By carefully analyzing the spectrum, scientists can build a temperature profile showing how hot the atmosphere is at different altitudes. This helps us understand the physics of how energy flows through the planet. There is also the possibility of detecting weather patterns. If this world has large-scale atmospheric features, storms or bands or spots, analogous to Jupiter's Great Red Spot, these might cause small variations in the transit light curves. Different transits might look slightly different as different parts of the atmosphere pass in front of the star. Detecting these variations would give us a glimpse of the planet's weather. Ground-based telescopes can contribute too. High-resolution spectroscopy can detect the Doppler shift of atmospheric gas as the planet orbits. This technique can identify molecules in the atmosphere even when they produce only subtle spectral features. It can also measure wind speeds in the atmosphere by detecting the shift in spectral lines as gas moves toward or away from us. Continued monitoring of the system might reveal additional planets. Most planetary systems have more than one planet. Our solar system has 8. Some exoplanetary systems have 5, 6, or more known planets. If there are additional planets around this star, they might produce additional transit dips, or they might cause small variations in the giant's orbital timing as their gravity tugs on it. There is even a chance of detecting moons. If this planet has large moons, they could produce their own transit signatures. Detecting an exomoon would be incredibly exciting, a whole new class of object to study. So far, despite extensive searches, we have not confirmed any exomoons, but planets like this one, with their deep transits and long observation histories, are among the best places to look. The science is far from finished. Every observation adds to our understanding. Every measurement constrains our models. The planet has been studied for nearly a decade since its announcement, and it will continue to be studied for decades to come. The future holds even more powerful tools. The European Extremely Large Telescope, currently under construction in Chile, will have a mirror nearly 130 feet across. It will be able to directly image some exoplanets and study their atmospheres in unprecedented detail. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-20s, will search for exoplanets using gravitational microlensing, a technique that can find planets far from their stars that other methods miss. Each new telescope and each new technique adds to our understanding. This planet, discovered with relatively modest ground-based telescopes, will be studied with the most advanced instruments humanity has ever built. That is the nature of science. Discoveries build on discoveries. Questions lead to more questions. Every answer reveals new mysteries. Stepping back now to consider the broader context of what we have learned tonight. Before 1995, we knew of exactly 0 planets beyond our solar system. We had theories, speculation, and hopes, but no confirmed discoveries. Today, just a few decades later, we have confirmed over 5,700 exoplanets. Thousands more candidates await confirmation. We have found planets of every conceivable type, from rocky worlds smaller than Earth to gas giants larger than Jupiter, from planets that orbit their stars in just a few hours to planets that take centuries to complete one orbit. We have found planets in the habitable zone of their stars, where liquid water might exist on the surface. We have found planets orbiting binary stars, with 2 suns in their sky. We have found planets that orbit so close to their stars that their surfaces are molten. We have found rogue planets wandering through space without any star at all. The discovery of so many exoplanets has taught us that planetary systems are common. Almost every star you see in the night sky probably has at least one planet. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. If most of those stars have planets, that means there are likely hundreds of billions of planets in our galaxy alone. And there are at least 2 trillion galaxies in the observable universe. The total number of planets is almost beyond comprehension. Somewhere out there, among all those worlds, there might be life. This is one of the driving motivations behind exoplanet research. We want to find Earth-like planets, worlds with the right conditions for life as we know it. This giant world is not such a place. It is a gas giant with no solid surface, temperatures that would destroy any life we can imagine, and an atmosphere dominated by hydrogen and exotic vapors. Life, as we know it, could not survive there. But studying planets like this one helps us understand planetary systems as a whole. Hot Jupiters probably did not form where we find them today. They likely formed in the outer regions of their planetary systems and then migrated inward over millions of years. This migration can dramatically reshape a planetary system, pushing smaller planets into new orbits or even ejecting them from the system entirely. Understanding how hot Jupiters form and migrate helps us understand which types of planetary systems might be hospitable to life. If hot Jupiter migration is common and violent, it might clear out the inner regions of many planetary systems, destroying any Earth-like planets that might have formed there. If migration is rare or gentle, more planetary systems might harbor rocky worlds in habitable zones. This discovery is a piece of a much larger puzzle, a data point that helps us map the incredible diversity of planetary systems throughout the universe. What would it actually be like if you could somehow visit this world, even though such a journey is utterly impossible with current technology? The journey itself would be a challenge beyond anything humanity has ever attempted. At over 1,000 light-years distance, traveling at the speed of Voyager 1, about 17 miles per second, the trip would take over 11 million years. That is longer than modern humans have existed as a species. But imagine you could somehow make the journey instantaneously, like in science fiction stories. What would you find? Approaching the system, you would first notice the star itself. It is hotter and brighter than our own stellar neighbor, appearing intensely white, perhaps with a slight bluish tinge. The radiation output is much higher, flooding the entire planetary system with energy. As you drew closer to the giant world, you would begin to appreciate its scale. From 1,000,000 miles out, it would appear as a distinct disk rather than a point of light. From 100,000 miles, it would fill a large portion of your view, a curved surface stretching across your field of vision. The colors would be unlike anything in our solar system. Jupiter has its distinctive bands of brown, tan, cream, and rusty red, created by different chemical compounds at different altitudes being stretched into parallel stripes by the planet's rapid rotation. This world might have similar banding, or it might appear more uniform, or it might display patterns we have never seen before. If you could somehow descend into the atmosphere, conditions would become increasingly extreme. Near the cloud tops, temperatures are already severe. As you descended, pressure would increase. The atmosphere would become denser and denser. Light from the star would fade into a perpetual twilight, and then into darkness. There is no surface to land on. Unlike rocky planets with distinct solid surfaces, gas giants are composed almost entirely of gas and fluid. As you descend, the atmosphere simply becomes progressively thicker and hotter. Eventually, the pressure becomes so extreme that the distinction between gas and liquid breaks down entirely. You would be immersed in a supercritical fluid, a phase of matter with properties intermediate between gas and liquid. Deeper still, if you could somehow survive the crushing pressure and blistering temperature, you might encounter stranger things. In the cores of some gas giants, hydrogen is compressed so tightly that it becomes metallic. Whether this world has such a layer is uncertain. Its extremely low density suggests that whatever core it has must be small or diffuse. Understanding the internal structure of this world is one of the great challenges of studying it. We cannot see inside. We can only measure the planet's total mass, size, and behavior, and from these, infer what might be happening in the deep interior. Different models make different predictions. Future observations might help distinguish between them. This giant planet is part of a broader lesson that modern astronomy has taught us. The universe is far stranger and more varied than we imagined when we only knew our own solar system. Every type of planet we thought we understood has turned out to have variations we never expected. Gas giants can be cold and far from their stars like Jupiter and Saturn, or scorching hot and close like hot Jupiters. They can be dense and compact, or puffy and inflated. They can be alone or have companions. They can migrate, collide, be ejected into interstellar space. Rocky planets can be smaller than Earth, or several times larger. They can be dry and barren, or covered in water, or shrouded in thick atmospheres of carbon dioxide or nitrogen or exotic gases. They can orbit in the habitable zone, or much closer, or much farther from their stars. Ice giants like Uranus and Neptune have their own variations. Some exoplanets seem to be water worlds, with deep oceans covering rocky cores. Others might be made mostly of carbon, with surfaces of diamond under extreme pressure. The diversity is staggering. And every time we develop new instruments or new techniques, we find things we did not expect. The universe continues to surprise us. This discovery is part of that ongoing surprise. The largest confirmed planet, a world so inflated that it would float in water despite being larger than any other planet we have found. An example of the strange possibilities that emerge when planetary physics operates under extreme conditions. The search for exoplanets is one of humanity's great adventures. We have gone from knowing only the planets of our own solar system to cataloguing thousands of worlds around other stars in just a few decades. We have developed techniques to study the atmospheres of planets light years away. We have found planets in the habitable zones of their stars, places where liquid water might exist on the surface. We have expanded our understanding of what planets can look like and how they form. This discovery is one landmark on that ongoing journey. It holds the current record for largest confirmed planet by radius. But beyond the record, it is a world that teaches us about the diversity of planetary systems, the processes that shape gas giants, and the extremes that exist in the universe. I want to address something that often comes up when discussing discoveries like this one. Some people ask, what is the point? Why spend time and resources studying a planet we can never visit, never touch, never experience directly? These are fair questions, and they deserve thoughtful answers. First, there is the simple human drive to know. We are a curious species. We want to understand the world around us, including the universe beyond our world. This curiosity has driven every scientific advance in history. The same curiosity that makes us wonder about distant gas giants is the curiosity that led to every technology you use, every medicine that keeps you healthy. Knowledge has intrinsic value. Understanding the universe better is its own reward, regardless of practical applications. When we learn about a giant planet orbiting a distant star, we are adding to the sum total of human knowledge. That has value even if it never leads to any practical technology. Second, studying exoplanets teaches us about planetary physics in ways that studying our own solar system cannot. We only have one solar system to examine up close, and it contains a particular set of planets in particular configurations. We might think Jupiter represents what gas giants are like, but without other examples, we cannot know what aspects of Jupiter are universal and what aspects are specific to its history and environment. Exoplanets give us that broader context. By studying hundreds of gas giants across many different systems, we learn which properties are common and which are rare. We discover phenomena like extreme inflation that do not occur in our solar system. We test our theories against a much larger sample. This makes our understanding of planetary science stronger and more complete. Third, the technologies developed for exoplanet research often have broader applications. The precision measurement techniques used to detect tiny brightness dips have applications in medical imaging, manufacturing, quality control, and other fields. Science has a long history of basic research leading to unexpected practical benefits. Fourth, and perhaps most importantly, studying exoplanets is part of the larger quest to understand our place in the universe. Are we alone? Is Earth unique? Or are there other worlds like it? Could life exist elsewhere? These are some of the deepest questions humans have ever asked. Exoplanet research brings us closer to answering them. This giant planet itself is not a candidate for hosting life, but understanding planets like this one helps us understand planetary systems as a whole. It helps us identify which types of systems are likely to have habitable planets and which are not. Every piece of the puzzle matters. There is also something to be said for inspiring the next generation. Young people today will grow up in a world where thousands of exoplanets are known, where astronomers can study the atmospheres of distant worlds, where the search for life beyond Earth is an active scientific program rather than a dream. Some of those young people will become the astronomers who make the next great discoveries. They will build the telescopes that peer deeper into the cosmos, develop the techniques that reveal more about distant worlds, ask the questions we have not yet thought to ask, inspiring them, showing them that the universe is full of wonders waiting to be understood, is itself a valuable outcome of research like this. This planet is one of those wonders, a world that challenges our models, that stretches our understanding of what is possible. Every child who learns about it learns that the universe is bigger and stranger than they realized. Every atom in your body was once part of a star. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was forged in the cores of stars that died billions of years ago. Those stars exploded, scattering their atoms across space. Those atoms drifted through the cosmos for eons, before eventually coming together to form our solar system, our planet, and ultimately you. You are made of star stuff. This is not poetry or metaphor. It is literal truth. The elements heavier than hydrogen and helium that make up your body could only have been created in the intense heat and pressure of stellar cores or stellar explosions. And this giant planet we have been discussing tonight is made of the same stuff. Its hydrogen atoms are identical to the hydrogen atoms in water. Its helium atoms are the same helium that fills birthday balloons. At the most fundamental level, there is no difference between the matter that makes up this distant world and the matter that makes up you. We are connected to the cosmos not just through observation and understanding, but through our very substance. We are part of the universe, not separate from it. When we study distant planets, we are in a sense studying ourselves, or at least the same materials and processes that gave rise to us. This is perhaps the deepest lesson of modern astronomy. We are not spectators watching a distant show. We are participants in a cosmic story that began with the Big Bang and continues to this day. The same physics that governs the behavior of distant gas giants governs the behavior of cells in our bodies. The same gravity that holds planets in their orbits holds us to the surface of Earth. Understanding this connection changes how you see the world. It makes the universe feel less alien, less separate from everyday experience. It reveals that everything is part of one vast, interconnected whole. So as you go back to your daily life, carry a bit of this with you. Remember that somewhere out there, over 1,000 light years away, a planet twice the size of Jupiter is orbiting its star. It was there before humans existed and will be there long after we are gone. It does not know or care about us, but we know about it. We care about it. And in that knowing and caring, we transcend our small place in the universe, if only for a moment. Humanity stands at a unique moment in history. We are the first generation to know for certain that other worlds exist around other stars. We are the first to begin cataloging the planets of other solar systems. We are the first to study the atmospheres of worlds we will never visit. This knowledge changes how we see ourselves. We are not alone in a universe of barren stars. We are part of a cosmos teeming with worlds, many of them unlike anything in our experience. Some of them potentially similar enough to harbor life. The universe is waiting. It has always been waiting. And now, at last, we are beginning to explore it. Thank you for joining me on this journey. If you found it valuable, please consider supporting the channel. Every like, every subscription, every share helps me continue making these deep explorations of the cosmos. Look up at the stars when you get a chance. Think about the planets that might orbit them. Wonder about what is out there. That wonder, that curiosity, that openness to the vast unknown, these are among the best qualities we possess. Good night, and may you never look at the stars the same way. But before we truly end, some additional context makes this discovery even more fascinating. The history of how we learn to find planets around other stars is a story of persistence, ingenuity, and repeated failure before eventual success. For decades, astronomers tried every technique they could think of, and for decades, they came up empty. In the 1940s and 50s, some astronomers claimed to have detected planets around nearby stars using a technique called astrometry, which involves measuring tiny wobbles in a star's position as it moves across the sky. The most famous of these claims involved Barnard's star, one of the closest stars to our solar system. Peter van der Kamp, a Dutch astronomer working in Pennsylvania, spent decades collecting data and eventually announced that Barnard's star had two Jupiter-sized planets orbiting it. His announcement generated enormous excitement. If the nearest stars had planets, then planets must be everywhere. But as other astronomers tried to verify his results using different telescopes, they could not reproduce his findings. It gradually became clear that the wobbles van der Kamp had measured were caused not by planets, but by adjustments to the telescope itself. Every time the telescope was modified or repaired, it introduced tiny systematic errors that mimicked the signal of an orbiting planet. Van der Kamp never accepted that his planets were not real. He continued defending his results until his death in 1995, the same year that the first confirmed exoplanet around a sun-like star was announced. He missed by months the vindication that planets really do exist around other stars, though not around the particular star he had studied. This cautionary tale hung over the field for decades. Astronomers became extremely careful about claiming planet detections. They demanded multiple independent confirmations using different techniques. They scrutinized every possible source of systematic error. The false positive around Barnard's star had taught them how easy it was to fool themselves. This is why the announcement of 51 Pegasi b in 1995 was so carefully vetted. Michel Mayor and Didier Queloz had detected the planet using the radial velocity method, measuring the Doppler shift in the star's light as it wobbled back and forth. But they knew that other phenomena could mimic this signal. Stellar pulsations, spots on the star's surface, or unseen stellar companions could all produce similar patterns. They collected data for months, checking and rechecking their results. They looked for correlations with the star's activity cycles that might indicate the signal was coming from the star itself rather than an orbiting planet. They calculated and recalculated their uncertainties. Only when they were confident that no alternative explanation could account for the data did they announce their discovery. Even then, there was skepticism. Geoffrey Marcy and Paul Butler American astronomers who had been searching for exoplanets using similar techniques initially doubted the result. A Jupiter-mass planet orbiting in just 4 days? It seemed impossible. But when they turned their own instruments toward 51 Pegasi, they confirmed the result within days. The planet was real. This culture of careful verification persists in exoplanet science today. When the HAT network detected the transit of the giant planet we have been discussing tonight, they did not immediately announce a discovery. They collected more data. They conducted follow-up observations with larger telescopes. They measured the star's radial velocity to confirm that something massive was orbiting. They checked for any indication that the signal might be caused by something other than a planet. Only after all of these checks were completed, years after the initial detection, did they announce the discovery. This careful approach is why we can have confidence in the results. The planet is real because multiple independent techniques all point to the same conclusion. This story of careful science, of false starts and eventual success, of the hard work required to separate real discoveries from artifacts and errors, is part of what makes exoplanet research so compelling. It is not easy. It requires patience, rigor, and a willingness to be proven wrong. But when a discovery survives all of that scrutiny, you can trust it. Other record-holding planets provide important context and comparison for this discovery. The hottest known exoplanet is Kelt 9b, which we mentioned earlier. Its dayside temperature exceeds 4,300 Kelvin, or about 7,600 degrees Fahrenheit. That is hotter than the surface of many stars. At these temperatures, molecules break apart into their component atoms. The atmosphere contains atomic hydrogen, atomic helium, atomic iron, and atomic magnesium, all floating as individual atoms rather than combined into molecules. Kelt 9b is so hot that it is slowly evaporating, losing mass to space as its atmosphere is stripped away. The coldest known exoplanet is harder to pin down because very cold planets are extremely difficult to detect. But OGLE 2005 BLG 390 liters b, discovered through gravitational microlensing in 2005, is estimated to have a surface temperature of about -364 degrees Fahrenheit, or about 50 Kelvin. That is colder than Pluto. It orbits far from its host star, a small red dwarf, receiving little warmth. It is almost certainly a frozen, lifeless world. The densest known exoplanet is a matter of some debate, but candidates include Kepler 131c, which may have a density exceeding 30 grams per cubic centimeter. For comparison, iron has a density of about 7.9 grams per cubic centimeter, and lead is about 11.3. A planet with density exceeding 30 would be made of something exotic, perhaps compressed heavy elements under enormous pressure. We do not fully understand how such dense planets form. The least dense known exoplanet, aside from the giant we have been discussing, is WASP 193b, which has a density of about 0.059 grams per cubic centimeter. That is slightly less dense than our record holder. The two planets are remarkably similar in their puffiness, and understanding why some hot Jupiters inflate to such extreme degrees while others remain more compact is an active area of research. The planet with the shortest orbital period confirmed around a main sequence star is K2 137b, which orbits its star in just 4.3 hours. It completes more than 5 orbits every Earth day, whipping around its star at tremendous speed. At such close range, it must be tidally locked with one hemisphere perpetually roasting and the other in permanent darkness. The planet with the longest orbital period is harder to determine, because planets in wide orbits are very difficult to detect. They transit rarely, if at all, and their gravitational influence on their stars is weak. But some directly imaged planets orbit at distances of hundreds or thousands of astronomical units, taking thousands of years to complete a single orbit. These distant giants likely form differently than closer-in planets, perhaps through direct gravitational collapse rather than core accretion. Each of these extreme planets teaches us something. The hottest planets show us how atmospheres behave at temperatures that break apart molecules. The coldest planets show us what happens when a world receives almost no stellar energy. The densest planets challenge our understanding of planetary interiors. The least dense planets, like our subject tonight, challenge our understanding of atmospheric physics and energy transport. Together, these record holders define the boundaries of what is possible for planets. They mark the extremes of the planetary population, the edges of the distribution. Understanding these extremes matters because they constrain our theories. Any successful model of planet formation and evolution must be able to explain not just typical planets, but also these outliers. The host star itself deserves closer attention, because the properties of the star are key to understanding the planet. F-type stars like this one occupy a particular niche in the stellar hierarchy. They are more massive than our star, which is a G-type, but less massive than A-type stars. They are hotter, with surface temperatures between about 6,000 and 7,500 Kelvin, compared to our star's 5,800 Kelvin. They are more luminous, putting out several times more energy than our stellar neighbor, but they are also shorter-lived. The more massive a star is, the faster it burns through its nuclear fuel. Our star will last about 10 billion years on the main sequence, the stable phase of hydrogen burning. An F-type star like this one might last only 5 to 7 billion years. And at the end of its life, it will swell into a red giant, potentially engulfing close-in planets. F-type stars are interesting targets for exoplanet searches because they are bright enough to study in detail, but not so hot that their radiation overwhelms planetary signals. They are also fairly common, making up perhaps 3% of all stars in our galaxy. That may not sound like much, but with hundreds of billions of stars in the Milky Way, 3% is still billions of F-type stars. The rotation rate of this particular star is also relevant. Rapidly rotating stars are harder to study with the radial velocity method because their spectral lines are broadened and blurred by the rotation. This star rotates relatively slowly, which made it easier to measure the tiny Doppler shifts caused by the orbiting planet. The chemical composition of the star, particularly its metallicity, which astronomers use to describe the abundance of elements heavier than helium, can also influence planet formation. Stars with higher metallicity tend to have more giant planets, probably because there was more solid material available in the protoplanetary disk to build planetary cores. This star has roughly solar metallicity, meaning its composition is similar to our stars. All of these stellar properties factor into understanding the planetary system. The star's luminosity determines how much energy the planet receives. Its age tells us how long the planet has had to evolve. Its rotation and activity influence how easily we can detect and characterize the planet. Stars and planets are intimately connected, and understanding one requires understanding the other. Theoretical work over the past decade has tried to explain inflated hot Jupiters like this one. When the first inflated hot Jupiters were discovered, they posed an immediate puzzle. Standard models of planetary structure predicted that gas giants should have a certain size for a given mass. Jupiter, for example, is very close to the predicted size for a planet of its mass and age. But the new hot Jupiters were too big. Something was puffing them up beyond what the models allowed. The most obvious explanation was the intense stellar heating. These planets orbit so close to their stars that they receive hundreds or thousands of times more radiation than Jupiter receives from our star. This energy heats the upper atmosphere, causing it to expand. Simple models incorporating this heating could explain some of the inflation. But for the most extreme cases, including our record holder, simple heating is not enough. The planets are puffier than even detailed models predict. Something else must be at work. One leading theory involves the transport of heat from the irradiated upper atmosphere down into the deep interior. In standard models, the energy deposited in the upper atmosphere mostly radiates back into space without penetrating very deep. But if some mechanism can transport a fraction of that energy into the planet's interior, it would inflate the planet from within. What could cause this deep heating? One possibility is called ohmic dissipation. The intense stellar radiation ionizes the upper atmosphere, creating a conducting layer. As atmospheric winds blow this conducting material through the planet's magnetic field, electrical currents are induced. These currents dissipate energy as heat deep within the planet, keeping the interior hot and inflated. Another possibility involves the coupling between atmospheric circulation and interior dynamics. The extreme temperature difference between day and night sides drives powerful atmospheric flows. These flows might interact with deeper layers of the planet, transporting angular momentum and energy in complex ways that keep the interior from cooling and contracting as it otherwise would. A third possibility is that the planets have unusual atmospheric compositions that affect how efficiently they radiate energy. If certain molecular species at specific altitudes absorb and re-emit radiation in ways that trap heat, the planet could maintain a higher internal temperature than expected. Recent work has suggested that the truth may involve a combination of all these mechanisms, with different factors being more or less important for different planets depending on their specific properties. The field is still working toward a unified understanding. Computer simulations are central to this research. Scientists create detailed three-dimensional models of planetary atmospheres, tracking how energy flows, how winds develop, how chemistry evolves. They simulate the interiors of these planets, modeling how heat is transported from core to surface and how the structure responds to external heating. By comparing these simulations to observations, they can test which theoretical mechanisms best explain the data. Our record-holding planet is a valuable test case for these simulations because it is so extreme. Any theory that successfully explains typical hot Jupiters must also be able to explain this outlier. If a model cannot reproduce the extreme inflation we observe, it is missing something important. This discovery also connects to our search for life elsewhere in the universe, even though the connection is indirect. At first glance, this giant planet seems irrelevant to the search for life. It is a gas giant with no solid surface. Its temperatures would destroy any organic molecules. Its atmosphere contains hydrogen and exotic vapors, not the oxygen and water we associate with life. No known form of life could survive there, but the discovery is relevant in indirect ways. Understanding how planetary systems form and evolve helps us identify which systems are likely to harbor habitable planets and which are not. Hot Jupiters like this one probably formed far from their stars and migrated inward. This migration would have been catastrophic for any smaller planets in the inner solar system. Rocky worlds in the habitable zone would have been scattered, ejected, or swallowed as the giant plowed through. If hot Jupiter migration is common, many planetary systems may have been sterilized by migrating giants. The inner regions that might otherwise have hosted Earth-like planets were instead disrupted by the passage of massive worlds. Our own solar system does not have a hot Jupiter. Jupiter and Saturn formed in the outer solar system and stayed there. This stability may have been necessary for the emergence of life on Earth. If Jupiter had migrated inward early in solar system history, it might have scattered the material that formed Earth, preventing our planet from ever existing. Understanding which factors determine whether gas giants migrate helps us identify which types of systems are most likely to be habitable. Stars of certain masses, with certain metallicities, in certain galactic environments, may be more or less likely to host stable planetary systems. This knowledge guides the search for Earth-like planets. There is also the broader lesson that planetary systems can look very different from our own. For decades, astronomers assumed that other solar systems would resemble ours, with small rocky planets close in and gas giants farther out. Hot Jupiters shattered that assumption. They showed that planets can end up in configurations we never imagined. This opens our minds to possibilities we might otherwise dismiss. Perhaps there are habitable planets in unexpected places. Perhaps there are forms of life that do not require conditions we consider necessary. Perhaps the universe is even stranger than we think. By cataloging the diversity of planetary systems, we expand our conception of what is possible. We become more creative in thinking about where life might exist. We consider scenarios that would not have occurred to us if we only knew our own solar system. The more we learn about planets like this distant giant, the better we understand the range of possibilities. And that understanding, even when it involves inhospitable worlds, ultimately serves the search for life. Since the announcement in 2017, astronomers have turned many different instruments toward this star to learn more about its giant planet. Ground-based telescopes have refined measurements of the transit depth and timing. Space-based observatories have searched for variations that might indicate additional planets or moons. Spectrographs have probed the atmosphere for chemical signatures. The Hubble Space Telescope has observed transits of this planet, searching for water vapor and other molecules in the upper atmosphere. These observations are challenging because the signal is small, but Hubble's stability and sensitivity make it well suited for the task. The Spitzer Space Telescope, before it was retired in 2020, observed this planet at infrared wavelengths. Infrared observations are particularly valuable for hot Jupiters because they probe different layers of the atmosphere than visible light. Spitzer helped constrain the temperature structure of the atmosphere and the efficiency of heat transport from day to night sides. Now, the James Webb Space Telescope is poised to take exoplanet characterization to a new level. JWST has already demonstrated its capability to detect specific molecules in exoplanet atmospheres with unprecedented precision. Its observations of this giant planet, when they occur, will reveal details about atmospheric composition, temperature profiles, and possibly even weather patterns. Ground-based telescopes continue to contribute as well. High-resolution spectrographs can detect individual spectral lines from atmospheric molecules, revealing not just what is present, but how it moves. By measuring Doppler shifts in these lines, astronomers can map wind patterns in the atmosphere, tracking how gas flows from day to night and from equator to poles. Photometric monitoring searches for variations in transit depth or timing that might indicate the presence of additional bodies in the system. A moon orbiting the giant planet would produce a distinctive signature, as would another planet perturbing its orbit. So far, no such signals have been detected, but the search continues. The accumulated data from all these observations has refined our understanding of the planet. The mass measurement has been improved from the initial estimate of about 1/3 Jupiter masses to the current best value of about 0.45 Jupiter masses. The radius has been measured more precisely. The orbital parameters have been pinned down with greater accuracy. Science advances through this kind of incremental refinement. Each new observation adds a bit more information. Measurement uncertainties shrink. The picture becomes clearer. What was once a fuzzy detection becomes a well-characterized world. This process will continue for years to come. Future telescopes will provide even better data. New techniques will extract more information from existing observations. Our understanding of this planet will continue to deepen, and eventually what we learn here will be applied to other planets. The lessons from studying this extreme case will inform how we study more moderate worlds. The techniques developed to probe this atmosphere will be refined and used on smaller, cooler planets, perhaps even Earth-like planets in habitable zones. That is the trajectory of science. Each discovery leads to the next. Each technique opens new possibilities. What seems like an end point is really a beginning. The transit method is surprisingly powerful for both discovering and precisely characterizing planets in detail. When a planet transits its star, it does more than just dim the starlight. The pattern of dimming encodes information about the planet's size, orbit, and even atmosphere. The depth of the transit tells you the size ratio between planet and star. A bigger planet blocks more light. By measuring the depth precisely, you can calculate the planet's radius relative to the star's radius. If you know how big the star is, which can be determined from other observations, you can calculate the planet's actual size. The duration of the transit tells you about the orbital geometry. A transit across the star's equator lasts longer than a grazing transit that just clips the star's edge. By measuring the duration and comparing it to the orbital period, you can constrain the inclination of the orbit and the impact parameter, which is how close to the star's center the planet passes. The shape of the transit, how the brightness changes as the planet enters and exits the stellar disk, reveals even more. Stars are not uniformly bright across their surfaces. They are brighter in the center and dimmer near the edges due to an effect called limb darkening. The transit light curve is shaped by this limb darkening, and by modeling it carefully, astronomers can learn about both the star and the planet. Transmission spectroscopy takes this further. By observing the transit at many different wavelengths, you can measure how the transit depth changes with color. If the planet's atmosphere contains molecules that absorb certain wavelengths, the planet appears slightly larger at those wavelengths because the atmosphere is effectively opaque. By mapping out these variations, you can identify which molecules are present. Eclipse spectroscopy provides complementary information. When the planet passes behind the star, its light disappears. By comparing observations during and outside of eclipse, you can isolate the planet's own light. This tells you about the planet's temperature, the composition of its dayside atmosphere, and how efficiently heat is redistributed around the planet. Phase curves track how the planet's brightness changes throughout its orbit. As the planet orbits, we see different portions of its surface. The day side is brightest when the planet is on the far side of its orbit and we see it fully illuminated. By measuring these brightness variations, astronomers can map the temperature distribution across the planet and track atmospheric dynamics. All of these techniques have been applied to hot Jupiters like our record holder. Together, they build a remarkably detailed picture of worlds we have never visited and never will visit. From patterns of light alone, we can deduce sizes, masses, temperatures, compositions, wind patterns, and more. This is the power of precision measurement. With careful observation and clever analysis, we can learn about things far beyond our direct reach. The future of exoplanet science is extraordinarily bright. New missions are being planned that will discover thousands more planets. New telescopes will characterize their atmospheres in unprecedented detail. New techniques will enable observations that seem impossible today. The Plato mission, scheduled to launch in 2026, will search for Earth-like planets, around Sun, like stars. It will find planets in the habitable zones of stars, similar to our own, prime targets for follow-up observations to search for signs of life. The Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or ARIEL, will launch in 2029 to study the atmospheres of about 1,000 exoplanets. It will build a statistical picture of how atmospheric properties vary with planet type, providing context for individual discoveries like our record-holding giant. On the ground, the extremely large telescopes under construction will revolutionize direct imaging of exoplanets. They may be able to see Earth like planets around nearby stars, directly imaging worlds that might harbor life. These advances will build on what we have already learned. The hot Jupiters discovered today are laying the groundwork for the Earth, like planets of tomorrow. The techniques being refined on giant worlds will eventually be applied to smaller, more challenging targets. Science builds on itself. Every discovery creates the foundation for the next. The giant planet we have discussed tonight is part of this ongoing project, a step on the path toward understanding planetary systems in all their diversity. Someday, perhaps, we will find a planet that shows signs of life, some atmospheric signature, some chemical disequilibrium, something that cannot be easily explained by geology or chemistry alone. That discovery will transform our understanding of our place in the universe. When that day comes, it will be built on decades of work characterizing planets of all types. The hot Jupiters, the super-Earths, the mini-Neptunes, the inflated giants, all of them contributed to the knowledge base that made the discovery possible. Even the most exotic, least habitable planets teach us something that matters. That is the nature of science. You never know which discovery will turn out to matter. You never know which technique developed for one purpose will prove useful for another. You follow curiosity where it leads, trusting that understanding is its own reward. This giant planet is part of that grand project. One world among thousands already discovered and millions yet to be found. A record holder today that may be surpassed tomorrow. A puzzle that may someday be fully solved or may remain partially mysterious forever. But whatever happens, it matters that we looked. It matters that we discovered it. It matters that we tried to understand. The universe is vast and mostly unknown, but every piece of knowledge we gain is a victory. Thank you once more for joining me on this exploration. The universe is full of wonders, and this is just one of them. Keep looking up, keep wondering, keep asking questions. The stars are waiting. A few more fascinating aspects of this particular discovery deserve attention before we conclude. The constellation Hercules, where this star resides, has been observed since ancient times. The Greeks named it after their legendary hero, the strong man who completed 12 impossible labors. The constellation contains some notable deep sky objects, including Messier 13, one of the brightest globular clusters visible from the northern hemisphere. Globular clusters are dense, spherical collections of hundreds of thousands of stars, ancient relics from the early universe that orbit our galaxy. But of course, the ancient Greeks knew nothing of the planet orbiting this particular star in Hercules. They did not even know that stars were distant suns. They thought the stars were lights fixed to a celestial sphere rotating around the Earth. The idea that stars might have their own planetary systems would have been almost unimaginable to them. It took millennia of accumulated knowledge to reach our current understanding. Copernicus moved Earth from the center of the universe. Galileo turned his telescope to the sky and saw moons orbiting Jupiter, proving that not everything orbited Earth. Newton explained gravity, allowing us to calculate orbits and predict positions. Spectroscopy revealed what stars are made of. Relativity refined our understanding of space and time. And finally, in the 1990s, we developed instruments precise enough to detect planets around other stars. Each step built on those before. Each generation of scientists inherited the tools and knowledge of their predecessors and pushed a little further. The discovery of this giant planet is the result of that accumulated effort, centuries of work by thousands of individuals who asked questions and sought answers. This perspective is worth keeping in mind. Scientific discoveries do not appear from nowhere. They are the product of long chains of investigation, each link dependent on those that came before. When we celebrate a discovery like this one, we are really celebrating the entire edifice of science that made it possible. The concept of the habitable zone connects to hot Jupiters in important and often overlooked ways that deserve explanation. The habitable zone is the region around a star where conditions might allow liquid water to exist on a planet's surface. Too close to the star, and water boils away. Too far, and water freezes solid. Only in the middle zone can liquid water persist, which is generally considered necessary for life as we know it. The exact boundaries of the habitable zone depend on many factors. The star's luminosity is the most important, with more luminous stars having wider and more distant habitable zones. But the planet's atmosphere matters too. A thick atmosphere with greenhouse gases can keep a planet warm, even if it receives less stellar energy. A thin atmosphere, or one without greenhouse gases, might be too cold, even within the traditional habitable zone boundaries. Hot Jupiters, like our record holder, orbit well inside the habitable zone. They are far too hot for liquid water, but studying them helps us understand how planets move within their systems and what configurations are stable. If a hot Jupiter is present in a system, the habitable zone is likely to have been disrupted. Any small rocky planets that might have formed there were probably scattered or ejected when the giant migrated through. Systems with hot Jupiters are probably not good places to look for Earth-like planets. Conversely, systems without hot Jupiters, where gas giants remained in the outer regions like in our solar system, are more promising. The inner solar system was not disrupted by migrating giants, allowing Earth to form and remain in a stable orbit within the habitable zone. This kind of reasoning helps astronomers prioritize targets for detailed study. With thousands of exoplanet systems known and limited telescope time available, you have to make choices about where to look. Understanding the dynamics of different system architectures helps make those choices wisely. The giant planet we have discussed tonight is part of the data set that informs these choices. By studying it and other hot Jupiters, we learn about migration, about system architecture, about what happens when giants wander. That knowledge guides the search for more promising targets. The amateur astronomy community also plays a valuable role in exoplanet science that deserves more recognition than it usually receives. Professional astronomers using major observatories make most exoplanet discoveries, but amateurs can and do contribute, particularly in follow-up observations that help confirm and characterize planets. Transit observations, in particular, are well suited to amateur participation. Once a transiting planet is discovered, its transits can be observed by anyone with a telescope and camera precise enough to measure small brightness changes. Amateur astronomers around the world have contributed transit observations that helped refine orbital parameters and search for timing variations. This distributed network of observers has real advantages. Professional observatories have limited time and many demands. Weather at any single site can prevent observations during key windows. But with amateur observers spread across continents, there is a good chance that someone, somewhere, will have clear skies for any given transit. Several organized programs coordinate amateur contributions to exoplanet science. These programs provide tools for data collection and analysis, maintain databases of observations, and connect amateurs with professional astronomers who can use the data. If you have a telescope and an interest in contributing to science, transiting exoplanets offer a genuine opportunity. You can observe real transits, collect real data, and contribute to real research. It is one of the few areas where amateurs can make meaningful contributions to professional astronomy. The giant planet we have discussed tonight has been observed by amateurs as well as professionals. Its relatively deep transit, about 2.5%, is detectable with modest equipment under good conditions. Amateur observations have helped refine the transit timing and confirmed the consistency of the signal over time. This collaboration between amateurs and professionals represents something beautiful about science. The universe belongs to everyone. Anyone with curiosity and patience can participate in understanding it. The boundary between amateur and professional is permeable, united by a shared interest in discovery. Mysteries still remain about this planet, and others like it. Despite years of study, we do not fully understand why some hot Jupiters are much more inflated than others. Planets with similar masses and temperatures can have very different radii. Some puff up enormously while others remain relatively compact. What determines which planets inflate and which do not? Part of the answer probably involves the planet's formation and migration histories. Planets that migrated early, when their stars were still young and active, might have experienced different heating than those that migrated later. The timing and path of migration could affect the final orbital configuration, which influences tidal heating. Differences in interior composition, the size and makeup of any core, could affect how the planet responds to external heating. But these explanations remain incomplete. The scatter in the radius-inflation relationship is larger than current models predict. Something is missing from our understanding. Another mystery involves the atmospheres of these planets. Observations have shown that hot Jupiter atmospheres are surprisingly diverse. Some are cloudy or hazy, with their spectral features muted by obscuring particles. Others are relatively clear, showing strong signatures of water, vapor, and other molecules. What determines whether a particular planet has clouds or haze? Cloud formation depends on temperature, pressure, and composition in complex ways. The vertical mixing in the atmosphere, how efficiently material is transported between different layers, affects where clouds form and how thick they become. Chemical reactions in the atmosphere can produce haze particles from simple molecules. Magnetic fields might influence atmospheric dynamics in ways that affect cloud coverage. Unraveling these mysteries requires both better observations and better models. The James Webb Space Telescope is providing observations of unprecedented quality. Theorists are building increasingly sophisticated simulations. Progress is being made, but big puzzles remain. Our record-holding planet, as one of the most extreme examples of inflation, is a valuable data point for this research. Whatever processes drive inflation must be operating at full strength in this planet. By studying it in detail, we may be able to identify which mechanisms are most important. There are broader philosophical implications worth considering carefully when we discover worlds so different from anything in our experience. Humans have always wondered about the nature of the cosmos and our place in it. Ancient civilizations created myths to explain the stars. Philosophers debated whether the universe was finite or infinite, whether other worlds existed, whether those worlds might be inhabited. For most of history, these were questions without answers. We could speculate endlessly about what might exist beyond Earth, but we had no way to know. The universe was a vast unknown, filled with imagination but empty of facts. Exoplanet discoveries have changed that. We now know that other worlds exist, not as speculation, but as measured fact. We know their sizes, their masses, their temperatures, their atmospheric compositions. We have replaced imagination with knowledge, and what we have found is stranger than most imaginations predicted. Gas giants in scorching orbits, planets that would float in water, worlds where iron rains from the sky. The universe is not a mere repetition of what we see nearby. It is endlessly varied, full of possibilities we never conceived. This realization changes things. It suggests that whatever else the universe contains, whether life or intelligence or things we cannot imagine, we should not assume it will resemble what we already know. The universe has already surprised us repeatedly. It will surely surprise us again. This openness to surprise is perhaps the most important attitude we can cultivate. Science advances by following evidence wherever it leads, even when it leads somewhere unexpected. The greatest discoveries often come from results that did not fit the prevailing theory, anomalies that demanded new explanations. Hot Jupiters was such an anomaly. They did not fit the prevailing theory of planet formation, which assumed gas giants must form far from their stars. Their discovery forced a revision of that theory, leading to our current understanding of planetary migration. The universe taught us something we did not know. What else might we learn if we remain open to surprise? What other assumptions might the universe overturn? We cannot know in advance. That is part of what makes science exciting. The future is genuinely unknown, full of discoveries waiting to be made. The timeline of exoplanet science offers perspective on where we might be heading in another few decades. The first confirmed exoplanet around a sun-like star was discovered in 1995. As of now, about 30 years later, we have confirmed over 5,700 exoplanets. The rate of discovery has accelerated dramatically, from a handful per year in the early days to hundreds or thousands per year with space telescopes like Kepler and TESS. If this pace continues, we might know of 50,000 or 100,000 exoplanets by the middle of this century. More importantly, we will know much more about the planets we have already discovered. Atmospheric characterization, which is currently possible for only a small fraction of known planets, will become routine. By then, we may have detected signs of life on another world, or we may have confirmed that life is rare, at least in our cosmic neighborhood. Either result will transform how we think about ourselves and our place in the universe. The giant planet we have discussed tonight will be a historical footnote by then, one of the early discoveries that helped shape the field. Future astronomers will look back at our current era as a pioneering time when we first began to explore the diversity of planetary systems. They will have tools and knowledge we cannot imagine, just as we have tools and knowledge that would astonish astronomers of a century ago. That is the trajectory of science. Each generation inherits from the past, contributes what it can, and passes the torch to the future. The discoveries we make today will enable discoveries we cannot foresee. The questions we answer will suggest questions we have not thought to ask. This is one of the most hopeful aspects of science. It is not static but growing, always advancing, always learning more. Whatever problems we face as a species, our understanding of the universe continues to deepen. That deepening understanding is a gift to future generations, even if we cannot predict exactly how they will use it. A meditation on perspective and our place in the larger cosmos seems fitting here. You are a conscious being living on a small, rocky planet orbiting an ordinary star in a galaxy containing hundreds of billions of stars. Your galaxy is one of trillions in the observable universe. The universe itself is nearly 14 billion years old and will continue for trillions of years more. In cosmic terms, your existence is brief and your scale is tiny. The planet we have discussed tonight could contain 12,000 Earths. The distance to it is so great that light takes a millennium to bridge the gap. The universe stretches far beyond, full of wonders we will never see. And yet here you are, a collection of atoms that has learned to think, to wonder, to ask questions about the cosmos that created it. That is strange. That is precious. That is the miracle hidden in the mundane fact of your existence. When you look up at the night sky, you are not merely observing distant lights. You are participating in a grand tradition of wonder that stretches back to the first humans who gazed at the stars and asked what they were. You are connected across time to every philosopher who pondered the cosmos, every astronomer who mapped the heavens, every scientist who sought to understand. And you are connected across space as well. The atoms in your body were forged in stars like the one this giant planet orbits. The hydrogen in your water is the same hydrogen that makes up most of this distant world. The iron in your blood was created in supernova explosions billions of years ago, scattered across space, eventually incorporated into the planet you call home. You are part of the universe. The universe is part of you. This is not metaphor, but literal truth, written in the atoms of your being. The giant planet orbiting a distant star does not know you exist. It will continue orbiting long after you are gone, indifferent to human affairs. But you know it exists. You have learned something about it tonight, added a small piece to your understanding of the cosmos. That knowledge connects you to that distant world in a way that matters, even if only to you. Science offers this kind of connection. It links us to things far beyond our immediate experience, expanding the boundaries of what we can know and think about. It takes us out of our small daily concerns and places us in the context of a vast, strange, beautiful universe. That context can be comforting or terrifying, depending on your temperament. But it is true, and truth has value. Understanding where we are and what surrounds us is better than not understanding, even when the understanding reveals our smallness. And perhaps there is also comfort in knowing that we are not alone in a dead universe. Planets are everywhere. Many of them are strange and hostile, but they are there, real places in the cosmic neighborhood. The universe is full of worlds, full of possibilities, full of things we have not yet discovered. What else is out there? What other wonders await? We cannot know until we look, and looking, always looking, is what humans do best. A few more details about the physics of gas giant planets are worth exploring in depth before we conclude. Gas giants like Jupiter, Saturn, and this distant record holder are fundamentally different from rocky planets like Earth. They are not scaled-up versions of our world with solid surfaces hidden under thick atmospheres. They are something else entirely, worlds where the distinction between atmosphere and interior becomes meaningless. On Earth, there is a clear boundary between the atmosphere above and the solid ground below. You can stand on the surface and look up at the sky. The atmosphere has a defined base, the place where air meets rock. This boundary is crisp and unambiguous. Gas giants have no such boundary. As you descend into a gas giant's atmosphere, the pressure gradually increases. The gas becomes denser and denser. Eventually, the density becomes so high that the gas behaves more like a liquid than a gas. But there is no sudden transition, no surface where you stop falling. The atmosphere simply grades continuously into the interior. This is why we talk about the radius of a gas giant as a somewhat arbitrary number. For Jupiter and Saturn, astronomers typically define the radius as the point where atmospheric pressure equals 1 bar, roughly Earth's sea level pressure. But this is a convention, not a physical surface. You could equally well define the radius at a different pressure level and get a different number. For hot Jupiters like our record holder, the situation is even more complicated. The intense heating from the nearby star puffs up the outer atmosphere, creating an extended envelope that grades gradually into space. Where exactly does the planet end and space begin? The answer depends on how you define it. These definitional ambiguities do not undermine the science. Astronomers are careful to specify what they mean and to use consistent definitions when comparing different planets. The key measurements, like transit depth and radial velocity amplitude, are well defined and unambiguous. The derived quantities, like radius and mass, are calculated in standardized ways that allow meaningful comparisons. But the ambiguity does highlight something important about gas giants. They are not solid objects with well-defined boundaries. They are extended structures, dense in the center and thin at the edges, with no clear dividing line between inside and outside. They are fundamentally different from the rocky world we call home. The internal structure of gas giants is an active area of research. For Jupiter, we have detailed constraints from the Juno spacecraft, which has been orbiting Jupiter since 2016 and measuring its gravitational field with extraordinary precision. The gravitational field reveals the distribution of mass within the planet, allowing scientists to infer the internal structure. Juno's measurements have revealed that Jupiter's interior is more complex than simple models predicted. Rather than having a neat core of heavy elements surrounded by a uniform envelope of hydrogen and helium, Jupiter appears to have a dilute core with heavy elements mixed throughout a large fraction of the planet's volume. The boundary between core and envelope is fuzzy, not sharp. We do not have similar measurements for exoplanets. We cannot send spacecraft to orbit them and measure their gravitational fields up close. We can only infer what we can from distant observations, primarily the total mass and radius. For our record-holding planet, the very low density suggests an unusual internal structure. If the planet had a large, dense core, its overall density would be higher. The low density implies that either the core is very small, or it has dissolved and mixed throughout the planet, or perhaps it never formed in the first place. Understanding why different planets have different internal structures is a key goal of planetary science. The answer likely involves the details of planet formation, how much solid material was available to form a core, how quickly the planet accumulated its gaseous envelope, and what happened subsequently as the planet cooled and evolved. The extreme heating from the nearby star complicates matters further. Heat flowing into the planet from above might affect how heat flows out from below. The thermal structure of the interior is connected to the energy budget at the top of the atmosphere. Models must account for this coupling, which adds complexity. All of this makes hot Jupiters valuable laboratories for planetary physics. They experience conditions we cannot replicate in the lab. By studying how they respond to those conditions, we learn about the physics of planetary materials, about how energy flows through these objects, about the processes that shape their structure. Computer simulations now play a central and increasingly important role in all of modern exoplanet science. Our understanding of planets is increasingly shaped by sophisticated computer models. These models simulate the physics of planetary atmospheres and interiors, tracking how energy flows, how chemicals react, how structures evolve. For atmospheric models, scientists divide the atmosphere into layers and track the physical and chemical state of each layer. They calculate how radiation from the star is absorbed and re-emitted. They compute how winds develop and transport heat and material around the planet. They follow chemical reactions that produce and destroy different molecular species. These simulations can be run for different planetary parameters, exploring how the atmosphere changes when you vary the temperature, the composition, the gravity, or other factors. By comparing the simulation results to observations, scientists can determine which conditions best match the real planet. For interior models, scientists solve equations describing how pressure and temperature change with depth, how heat is transported by convection and radiation, and how the planet contracts and cools over time. These models can track the planet's evolution from its hot initial state after formation to its current condition billions of years later. Combining atmospheric and interior models is challenging but important. The atmosphere sits atop the interior, and the two are connected. Heat from the interior flows up through the atmosphere and escapes to space. External heating from the star penetrates down into the atmosphere and possibly into the interior. Getting this coupling right is necessary for understanding planets like our record-holding giant. Modern simulations run on powerful supercomputers and incorporate increasingly realistic physics. They can now model three-dimensional atmospheric dynamics, track hundreds of chemical species, and resolve features at multiple scales. The results are often presented as simulated images or spectra that can be directly compared to observations. These simulations have been key for interpreting observations of hot Jupiters. When we detect a spectral feature indicating the presence of a certain molecule, simulations help us understand what that detection implies about the planet's overall composition, temperature structure, and atmospheric behavior. The interplay between observations and simulations drives progress. New observations reveal features that simulations must explain. Failed explanations point to missing physics that must be added to the models. Improved models make predictions that motivate new observations. This cycle continues, with understanding deepening at each iteration. Why do stories like this one matter in the larger scheme of things? We live in an age of information overload. News cycles spin faster than ever. Attention is fragmented across countless platforms and topics. It can be hard to focus on any one thing long enough to understand it deeply. But some things deserve deep attention. The universe is one of them. The discovery that other worlds exist, that planets orbit distant stars, that the cosmos contains variety beyond our imagination. This is one of the great revelations of our time. It deserves more than a passing glance. When you spend 2 hours learning about a single planet, you are doing something valuable. You are stepping outside the rush of daily life and engaging with something larger. You are exercising your capacity for wonder, for sustained attention, for deep thinking about things that matter. This planet will not solve any of your immediate problems. Knowing about it will not help you pay your bills or navigate your relationships or advance your career. In strictly practical terms, this knowledge is useless. But humans do not live by practical terms alone. We need meaning, beauty, wonder, connection to things larger than ourselves. We need to feel that the universe makes sense, or at least that we are trying to make sense of it. We need stories that expand our minds and challenge our assumptions. The story of this giant planet, the largest ever found, orbiting a star over 1,000 light-years away, is such a story. It takes you beyond the familiar, beyond the everyday, into a cosmos of staggering scale and diversity. It reminds you that the universe is bigger than human affairs, that wonders exist whether or not we notice them, that reality is stranger and more beautiful than we usually remember. Carrying this awareness with you enriches life. It provides perspective when daily troubles loom large. It offers material for reflection during quiet moments. It connects you to the long human tradition of wondering about the stars. So thank you for spending this time with me. Thank you for caring about a distant world you will never visit. Thank you for being curious about the universe. That curiosity is precious. It is the source of all our knowledge, all our progress, all our understanding. As long as we keep asking questions, keep looking up, keep wondering what else is out there, we are participating in something noble. The largest planet ever found is out there right now, orbiting its star, utterly indifferent to human affairs, but available to human understanding. That availability, that openness to inquiry, is what makes science possible. The universe does not hide from us. It simply waits for us to look. And when we look, we find wonders. Before I let you go, one final reflection. The planet we have discussed tonight has been orbiting its star for billions of years. Long before Earth existed, long before our solar system formed, this giant was already there, circling in its scorching orbit, utterly alone in the dark. And it will still be there long after human civilization has risen and fallen, long after whatever comes after us has had its turn. The planet does not measure time in human terms. It does not care about centuries or millennia. It simply exists, following the laws of physics, indifferent and eternal by any human measure. There is something both humbling and comforting in that thought. The universe does not depend on us. It was here before us and will be here after us. Our existence is a brief episode in a much longer story, a story that does not require our presence to continue. And yet, during our brief episode, we have managed to reach out across the light years and learn something about that distant world. We have added it to our catalogue of knowledge. We have given it a name, measured its properties, speculated about its nature. In some small way, we have made it part of our story too. That is what conscious beings do. We observe, we learn, we integrate what we find into our understanding. The universe may not need us, but we need it. We need to know where we are and what surrounds us. We need to understand. This giant planet, the largest we have ever found, is now part of human knowledge. Whatever happens to us, whatever the future holds, we will have known about it. That knowledge is an achievement, small in cosmic terms but real in human terms. I hope this journey has been meaningful for you. I hope you carry something from it into your days ahead. The stars will be there whenever you need them, waiting to remind you of the vastness and strangeness and beauty of reality. Good night, sleep well, and may you never look at the stars the same way again.